In this lecture, we're going to explore a little more how function calls are carried out and learn about the function call stack. Let's revisit our C++ program execution model a little bit because that's going to shed some light into how functions are really called. Suppose again we have our application binary lying somewhere on our file system. When we double click on that, it is going to be loaded by the operating system and it's going to live somewhere in our memory map. Suppose we have a section in the memory map for the binary representation of our program to be loaded in, and that's our program area here, and suppose that our program is going to live in this space. So this is what we have seen so far. But now that we have learned a little more about C++, I think it is time we updated our memory map a little bit. And we're going to take into account some other things we already know. For example, we know about the heap, which is a location in our memory map which is going to contain dynamic memory we can use through the new operator. We have the stack, which is going to be where our local variables are going to live in functions. But now we already know about static and global variables. We have learned about that in the last lecture. And we know that we also need to set up a location for our binary to be loaded in the memory map. So let's revisit how our program is loaded in memory. Again, the binary is lying somewhere on our drive, and when it is loaded, it is going to be loaded in the part of the memory map called the code section. This is the part where the binary representation of our program is going to be loaded when we double click on our program, for example. We are going to have another section in our memory map which is basically going to store static and global variables, and these variables need to live in their own section because they are special. Remember that these variables need to be alive throughout the entire life of the program, and to be able to guarantee that, the operating system needs to make sure that these variables live in a separate location from the stack and the heap. We can't really talk about more details about this, but I want you to be aware of the sections of your memory map. The part we're going to be using a lot in this chapter is the stack part here, which is going to be where our function calls are going to be carried out. But before we see any more details on this, let's learn about a data structure that we call a stack. A stack is a collection type we have in C++ from which we can only add or remove things from the top. And let's show you what I mean here. Here we have a single element 0 in our stack, but we can add something on top here. If we need to add something, we can add a second element. If we need to add more, we can add 3. If we need to add another element, we can add a 4 here. But we can't really add elements between other elements. For example, we cannot try and put something between 1 and 2 here. That's not going to be possible. A stack can only take new elements from the top, and you can only remove elements from the top. For example, we can remove 4, we can remove the 3, we can remove the 2, and this is really how a stack works. And a stack is said to be a last in, first out data structure, because the first element to get in is the last to get out. For example, the 0 element here is the first element to get in, but if you add new elements on top and you want to remove the 0 element, you have no choice but to remove all the other elements from the top and then get access to the element 0 and remove it. And if you remove the 0 element here, the stack is going to be empty and you can add other stuff. But the working mechanics of a stack can really be described as first in, last out. The first element to get in is going to be the last element to get out. Okay, now that you know about how a stack works, let's see how function calls are really carried out. Suppose we have this program here, and let's try to understand it before we go any further. We have two variables, a and b here, and we have another variable called summation, and we're going to call the function called sum and assign the return value of this function to our variable here. Let's look at the function sum here. It is going to take 2 parameters by value. It is going to set up another variable called result, and then the sum function is going to call another function called adjust. Adjust is going to take 1 parameter by reference. Notice the ampersand symbol here. This is going to be by reference. And once we hit the body of adjust, we're going to set up an adjustment variable, and we're going to add that to whatever we got as our input. And because input is a reference, we're going to be modifying whatever was passed to us. And the changes we do in the adjust function here are going to be visible to whoever calls the adjust function. So what this is really going to do, we're going to pass our two variables, a and b, to sum. We're going to hit the body of sum. We're going to add up a and b, and we're going to get a 22 here. Let's say that. And once we do that, we're going to call the adjust function on this result variable. Notice that we pass result here as a reference. So if we try to modify the parameter we pass in here or the argument, the changes are going to be visible in this result variable. This is what we want to do. And inside adjust, we're going to set up a variable called adjustment, and we're going to add that to our input reference here. So the changes we do here, we're going to take the value 22, which was in our input variable. We're going to add a 2, and the result is going to be stored back in our input here. Because input is a reference, the change is going to be visible in this result variable, and it is going to be changed to be a 24 here. I really hope this makes sense. So if sum returns, it is going to return the result as is. So what we return here is going to be a 24. And if we print out the sum here, we should see sum is 24. That's what we should print here. And then the main function is going to finish and our program is going to end. This is how this program is going to work. The moment we run this program, the operating system is going to load it, and the main function is going to be pushed on the function call stack. Remember that function calls happens in the stack section of your memory map. So if your program runs, the main function is going to be put to the bottom of the function call stack. And what we have here is what we call a function activation record. And this is something we have in our function call stack, which is going to contain our local variables. For example, we see in the main function here, we have two variables. We have a and b. A is going to contain 10 and b is going to contain 12. So if we hit this point here in the main function, before we call the sum function, this is the state we're going to have. A is going to contain 10, B is going to contain 12, and the summation variable is basically going to contain junk because we haven't really initialized that. Then we're going to call the sum function here. The CPU is going to notice that we are trying to call another function. What it is going to do is to add a stack frame on our function call stack. And the stack frame can contain a few pieces of information. It can contain the return value of the function that you want to call. It may contain the parameters that are passed to the function. In this case, we want to pass a and b as parameters. It may also contain the return address where we will come back to when the function we are about to call terminates. So this is our stack frame here. The return value is what we're going to get from the sum function when it is executed. The parameters are going to be a and b in this case. And the return address is going to be the address of the main function here. Once we have our stack frame on top, the main function is going to freeze and we're going to activate the sum function. What we have here is the activation record of the sum function. And again, in the activation record, we have the local variables we have in our sum function. Notice that it has passed the parameters by a value. So now inside the sum function, we have local copies of our arguments here. And x is going to be 10 because that's what was passed in the first parameter here. And y is going to be 12 because that's what we passed in the second parameter here when we called the sum function. We're also going to have a result variable, which is not initialized by now. So we are going to run this statement here, and in result, we're going to store the sum of x and y. If we do that, the result is going to be 22, as we see in our activation record here. Now the next thing we want to do is to call another function. And again, the CPU is going to see that we are about to go to another location by calling another function. It's going to insert a stack frame on the top of the stack. Again, the stack frame is going to contain the return value. In this case, we're going to have one parameter, and that's going to be a reference to the result variable here, because you notice the adjust function takes one parameter by reference. once we have our stack frame on top here, we're going to activate the adjust function here. Again, we're going to have the activation record of this function to the top of the stack, and we're going to have our local variables inside. You see we have the adjustment variable and we have the input variable. But the input variable is really a reference to the parameter that we pass to this function. And it really is a reference to the variable that we have in the sum function here, and that's going to be the result variable here. So if we modify the input, the changes are going to be visible even in this result variable here, because we passed the parameter by reference to the adjust function. I really want you to understand this. Okay, so what we're going to do in the adjust function is add the adjustment to the input, and the result of that is going to be stored in our input here. So we're basically going to erase the value we have in the result variable in the sum activation record, and we're going to change that to a 24, because 22 plus 2, that's going to be 24. Now, after we do this, the adjust function is going to be done, and it is going to be popped off the call stack. The CPU is going to look at the return address, and it is going to see that it is the address of the sum function. So we're going to fall back to the activation record of the sum function. Once that happens, we're going to basically be at this location here. We will have called the adjust function. So the sum function is just going to return and be popped off the call stack. Then we're going to have the stack frame, which is going to lead us back to the main function because of the return address we have in here. The return value is going to be 24 because that's what we stored in our stack frame here. The stack frame is going to be popped off the stack. Then we're going to activate the main function again. The return value is going to be stored in our summation variable. We're going to have a 24, and then we're going to print it out. This is really how function calls are carried out when you chain them like we are doing here. And why do you really need to care about this? Well, this is going to make you understand how local variables become alive and die, because local variables are scoped to the activation record, which is to the top of the stack. Your local variables are only going to be alive when the activation record of your function is to the top of the stack. Another benefit is now that it is going to be easier to understand why inline functions may be desirable. Because going through the overhead to add your function to the top of the stack to call it can be really expensive in CPU cycles. And sometimes you want to avoid that with inline functions if your CPU happens to agree to inline your function. This is something that should be clear now. And the most important benefit, in my opinion, is that you're going to really be able to understand how the debug process of your application works. And we're going to learn about how we can debug our C++ applications starting in the next lecture. But for now, I really hope you understand how the function call stack is carried out. Again, function calls are going to be using a memory section in your memory map, and that's going to be the stack section. We are going to stop here in this lecture. In the next one, we're going to see how you can debug your C++ applications, and the call stack that we know now is really going to become handy. Go ahead and finish up here and meet me there.